Hello, welcome to the final day of 2021's Advent of Code. So this is day 25, and it seems like usually on day 25 they give us a bit of an easier problem to finish off the year. So I'm just going to quickly go over a solution to day 25. We are trying to help sea cucumbers move so we can find a place to land our submarine. So the rules are pretty simple. Every step, sea cucumbers will move either to the right or down, depending on which direction they're facing. And there's just a couple of extra rules. One is that if there's something in front of them, they don't move. Like this, only the one in front will move because there's a blank space. The east-facing ones will always move first, and the south-facing ones move second. And that just has some interesting interactions where something like this, for example, where this one will not move, but this one will move. And then after that, because this one has moved, you'll see that even though it's blocking, this is blocking this, but so this guy does get blocked, but on the other side, this guy doesn't get blocked, but rather this guy, because this has already moved. Which leads into the final rule, third and final rule, is that the map is wraps around. So once you go off the right side, you come back in on the left side. So it's really relatively straightforward. We can dive straight into some code. First thing is I would use a two-dimensional array to store this. So we can just kind of put something like that together. I was thinking that because this is a relatively straightforward puzzle, I can demonstrate some of the a couple of interesting features of Go. But we'll start with just parsing this. So we're going to use test1 as our data, which is this state. It's nice and simple, so we can kind of just make sure we've got our implementation right. So we just loop over every character, ch character in each line or row. Here, we'll pre-allocate these. And then test1. Grid y is going to be a string slice, length of the row. And when we store these things, we can store the dots, but dots indicate empty things. So it's probably when something is empty, it's probably better to just use the 0 value of the type. And in the case of string, these are empty strings. So what I would like to do here is I'm going to say, as long as the character isn't a dot, so if it's a greater than sign or a v, then we will write it into the grid. Otherwise, we just leave it blank. And so this shows the reason why we pre-allocate these arrays, because then we can just write straight into the ones that we care about and ignore the rest. This needs a conversion. So we can do this, print out our grid, and we have the data. Now, of course, this is the wrong way around. It should be if it's not a dot, then we store it. Now, this is a bit hard to read, and so Go gives us an interface called stringer. I wonder if I can pull it up like this. No, undocumented. Maybe I can bring it up. No, I can't. No, I can't. Okay, maybe it's called something else. So to implement a string type, the string function for a type, we just need to give it an alias. So I'm going to call it grid. Now, because I've called it a grid, I need to make sure it actually is a grid internally. So Go knows that the grid type, this is the grid type, so that assignment works fine. And we can now implement a string function for it to return a string. Now, when it comes to building strings in Go, we use the builder strings.builder to help us build it. Probably something just like this, but in reverse now. Now, when I print, I want to print out the dots again, just to make it easier to read and easier to compare to the original. So for every row in the grid, And then for every character in the row, if it is a dot, we're going to write, no, if it's empty, we're going to write a dot. Otherwise, we're going to write the character. And then we just need a new line. And we return the string out of it. And now, because we've implemented a string function for the grid type and we're trying to print it out, we are going to get the string, just the grid just like that. Cool, so we've got our parsing and our printing sorted. So let's implement this sort of step. Yeah, this is another one of those puzzles where every step something happens. These are quite common in here. So I'm just going to make a step function. It's going to take in a grid. It's going to return a new grid. I think that's one of the important things with a lot of these sorts of puzzles when it comes to like Conway's Game of Life type puzzles, or just these things that change state based on the previous state. It's always easier to just create a new array to write your new state. Because your new state depends on the old state. And if you mutate the old state as you're updating a new state, things can get messy and you can make mistakes. And so let's just make, we're going to copy this again. We're just going to make a new grid first. We want to make sure that we've allocated it. Cool. To grid. We won't call this grid, we'll call this next. Like this. So that's just pre-allocating all the, so this is a blank grid now that we have. So what do we need to do? Let's just write it out like this. We need to loop over the each row and then each character. Now what do we care? Well, now what do we want? We want to just check. There are three cases. It's either going to be empty string, it's going to be a south-facing one, or it's going to be an east-facing one. I like to write it out like this because it's kind of easy to think about and reason as you go through it. Now, if the current grid cell is blank, we don't do anything. If the current cell is downward facing one, yes, so this is where the rules come into place, right? We want to do the east facing ones first and then the south facing ones. So I'm going to treat this as two separate steps. I'm going to do the east facing ones first. That's my first half step. And then I'm going to do the next half step, which is doing all the south facing ones second. So on the first half step, we ignore the south facing ones. And we just write them straight into the new grid. But when it's an east-facing one, here we need to check x plus 1. X plus 1, east-facing? Yes, x plus 1. Now, because the grid wraps, an easy way to implement wrapping is to just take the modulo of the size of the slice. So we want to say if the grid at the next value, whatever that is empty, then that becomes, in the next grid, that becomes the east-facing one. Otherwise, the east-facing one just stays exactly where it is, just like the south-facing one. So that should be the first half step. I'm not sure if I've missed anything. I'm just going to let that go. Let's see, where am I? These should be single equals, not double equals. So let's just check whether this first half step is doing the right thing. We'll just check real quick. This should move one across. It has moved one across. this and this should wrap, they have, and this should stay, it stays. So that's great. Now for the second half of this, we just want to do this whole thing again. To keep this simple, what I'm going to do is I'm going to rotate the grid again and make another brand new grid. Now, is this the most efficient way to do it? No, but I think as a theme, kind of my theme for all of these is we kind of favor correctness over efficiency in cases like this. And if we do this, we can be a lot more sure that we're not going to accidentally do some mutate something in the original grid that's going to mess up our state for the new grid. So we're just going to make a new grid and treat our half step here as our original grid and do the same thing, but this time we are looking at the south facing ones. So south facing means we care about y. Y means we need to flip these around like this, and these are south facing ones. So that's just updating that part of the code. And does that look like this? It does look like this. So to test this, we're going to step a few more times, 2, 3, 4 times. So we should end up with this grid. So let's just take a quick look. Do we? That looks, compared to me, that compares the same as the fourth one. So I think I'm pretty happy with that step function. So the next step of this program is to work out when things have stopped updating. Now that should be pretty straightforward to do. We just keep track of whether or not we've updated something. So here we've only updated something. Something has only moved if this is the case where it's moved. So we set moved to true here. And the same for the other half of the loop. So we've got a moved variable that keeps track of the moved. So when it comes to something like this, you can always return multiple values out of a function. And when it comes to things like this, where you're returning a bool, it's always good to use a named return value just to kind of make it easier to use in your documentation. Both of these will default to 0 values. So moved is going to start off as false. So we don't have to set it. We can just delete all those placeholders. So this will now return. Oh, I just need to say return here. So it says too many arguments in call to step. Here we have this. This is now returning grid bool, which is too much. So we're just going to use a counter here instead. The nice thing about using this sort of return value is that it fits really well into a for loop. So this is what you can do. You can say OK equals true. While OK, we're going to set grid and OK to step of grid. So I hope this makes sense. This is a for loop. We just initialize our OK to true, so we're going to keep looping. And as long as OK is true, as long as we have moved, we're going to keep looping and keep counting. So here we're going to print out the count, and we're going to print out the grid just so we can check what we have. I'm using the wrong data. This data, it looks like, will never stop moving, so we don't want to be using that. I believe this input is actually test2 here. So I'm just going to swap in test2. Oops. I have broken it, apparently. If GIDX. Okay, so this is not length of row, is it? This is length of grid. Oh, okay, I can't print 58 first, can I? That's going to mess up my grid. So it says after 58 cycles, it turns into, well, it turns into this, which, as far as I can tell, matches up with the examples example data. So it's a pretty simple algorithm. I'm quite happy with it. I'm just going to run it on my data, which means here, instead of test2, we are going to use data, which is just my test data, which is huge, but I get 579 out of that, and I've already submitted my answer. It was 579. And with the final one, this is actually the first year I've completely finished every single. I've solved both parts of every puzzle. So this is the first time I've gotten to the end. I have all the stars. I can remotely start the sleigh, and I've completed the challenge for this year, which I'm pretty stoked about. But I think back to just this particular problem. Yeah, it's just a nice way to finish off the entire series. And here, just showcasing a couple more of Go's kind of idioms, giving type aliases. I'm not sure that they're actually called that, but that letting us print stuff. And then just this sort of idiom of returning a bool in a multi-valued return, which lets us write these sorts of statements, which can be really easy to read. And it's very idiomatically Go. So it's a short video today. I hope you had fun doing these challenges this year. I certainly did. Some of them were quite hard this year, but just powering through it was a good feeling. It's a little bit past Christmas, but I hope you had a wonderful Christmas this year. And yeah, I'll see you again next year, hopefully. Thanks for joining me.